Oh, nice.
All right.
Okay. Proper scoring rules, they are a class of widely used. There is a literature on proper scoring rules. They are widely used in many areas. So in machine learning, they are used as loss function. So suppose you are learning a distribution. So the property of a loss function is the minimizer of the loss should be the true distribution where the samples are coming from. And in mechanism design, they are used to elicit information. Like, for example, in peer grading, where there is an instructor who lets students grade each other, we use proper scoring rules to score the students so that the student can give us their truthful evaluation and feedback on their peers' assignments. So the existing literature mainly focuses on the characterization of the properness, where properness here means truthfulness of the scoring rule, to make the agents report their belief distribution truthfully. But the thing is, not all proper scoring rules perform well, and this is the question we are looking at in our paper. We are taking our motivation from the peer grading application, and here's an example telling you why some scoring rules may not work well. This is our example. So we consider how do scoring rules incentivize effort in peer grading applications. So suppose there is a peer grader who has one assignment to grade. And on that grading task, there are n criteria for him to grade, like, say, writing, clarity, and how well the proof is. So each criterion may be in a binary, from a binary space, bad and good. And the peer has binary action space. Without any effort, the peer is simply not looking at the assignment. So the peer, in this case, only has prior knowledge. For example, that is the uniform distribution over bad and good. So that is half probability believing it is bad or good. After exerting an effort, that is, the peer is looking at the assignment and getting a high-dimensional signal about the quality of the assignment. The peer can have an updated posterior. So for example, the peer is learning the true quality with probability 1/2n, ID on each of the criteria. So after that, the peer reports the mean, the marginal mean, which is an n-dimensional vector of his belief. And the TA reveals the true quality of the assignment, which is an n-dimensional binary vector. The peer gets a score in 0 and 1. So there is one common practice, that is the separate quadratic scoring rule. By separate, we mean giving a separate score on each of the grading criteria. And by quadratic, we mean using the quadratic scoring rule to elicit the peer's belief. So we can calculate the expected score for the peer. If the peer is not exerting any effort, that is reporting prior belief 1/2 on each of the criteria, the peer can get an expected score as high as 3/4. But if the peer is exerting an effort, we calculate his expected score, which is only 3/4 plus 1/8n. So this is saying, in this example, if there are 3 criteria or maybe 5 criteria for the peer to report, the peer is only having an incentive of maybe 1/24 to exert the effort. So this is showing the separate quadratic scoring rule is not working well in terms of incentivizing effort. Like, if the peer is smart enough, he will find out the expected gain of exerting effort is too small for him to exert the effort. So even if we are using the optimal scoring rule, optimal separate scoring rule, that is still giving a separate score on each of the dimensions, the incentive is still as small as 1/2n. And when n is very large, the peer still does not have the incentive to exert effort. So in our paper, we propose an optimal scoring rule that can achieve a constant incentive in this case. So here's our problem. We want to use proper scoring rules to incentivize effort, which is saying we are doing optimization over scoring rules. We want to understand what kind of a scoring rule is a good scoring rule. So our paper considers a binary effort model, which is a natural first step to understand this question. So here's our model. We want to maximize the expected gain of exerting effort for an agent. So there is a state space, which can potentially be an n-dimensional space. For example, in the opening example, we see the state space is n-dimensional binary state space. And the peer has a prior, and the agent has a prior distribution, which is a distribution over the state space. We focus on eliciting the marginal mean from the peer. So the report space is an n-dimensional real value space. And we assume the agent has binary strategy space. Without any effort, the agent has belief, which is the prior distribution. And after exerting effort, the agent updates to a posterior distribution. And since the agent is doing Bayesian updating, there's randomness over the posterior. So there's we let f be the density function over posterior means. That is the agent's posterior belief. And after the state is realized, the agent is scored by a scoring rule, which is by comparing the agent's report R and the realized true state. So here's the definition of proper scoring rules. So we say a scoring rule is proper for eliciting the mean if, so on the left-hand side, this is the expectation of truthful score. This is saying from the agent's perspective, he is believing the distribution is G, and he's reporting the marginal mean of the distribution G. And he's getting expected score of this. And on the right-hand side, that is the non-truthful score, where the agent tries to report something else, say R in the report space. So this is the properness of scoring rule. So we want to optimize over the class of scoring rules that are proper. That is saying we want the agent to report truthfully. And also, since we're motivated by a peer grading example, that is in education, we want the score to be ex-post bounded. Like in the exam or when you are giving a grade, you don't want the score to be higher than 100 or something. So this is the mathematical definition of the program. So we are maximizing the expected difference of the agent reporting the posterior distribution from reporting the prior distribution. And two constraints. First, S is proper. And second, S, we normalize it to be bounded in 0 and 1. So in this talk, I will first give some preliminary knowledge about the properness of scoring rule. And then I will talk about the optimal single-dimensional problem. And I will go to our design of approximately optimal scoring rule for a multi-dimensional problem and show a comparison between separate scoring rule to the optimal scoring rule. And in the end, I will talk about some related work and conclusion. So here's the preliminary, the characterization of proper scoring rule for eliciting the mean. So a canonical scoring rule for eliciting the mean is defined by a convex utility function. So you know truthfulness is about convexity in the convex function when the agent is reporting truthfully. So and the set of subgradients of the convex function. So the scoring rule should have this form, where the first two terms is getting the subgradient line at the report on the convex function, and the third term is the normalization term. So the normalization term is not important because you can see when the agent is taking expectation, the expectation of normalization does not change with his report. So the normalization simply does not affect the truthfulness of the scoring rule. We take expectation when the agent is reporting truthfully. The expected score is simply the convex function at the report plus the expectation of the normalization. So we can think of this utility function as the expected utility when the agent is reporting truthfully. And with this characterization, we can simplify our objective. And here's another reason why the normalization function is not important, because it cancels out. So we only care about the convex utility function. And here's a geometric interpretation of the truthfulness. So we have a convex function, which is plotted in the black solid line. Suppose the agent believes the true distribution having mean theta. If he is reporting truthfully, he will get a utility at u of theta. And now, suppose the agent wants to deviate and report something else, say r. By the characterization, he is going to get a score on the subgradient line passing through r. And if we take expectation from the agent's true belief, theta, he's going to get a score, expected score on the linear line at the point theta. So this score is lower than the truthful score he's going to get. So this is why this kind of characterization is truthful. And now I will talk about single-dimensional scoring rules. So recall that our optimization is equivalent as designing a convex utility function to maximize the expected difference between reporting the posterior and reporting the prior. So in this plot, I showed two convex utility functions, where the dashed line represents any arbitrary convex utility function, and the black solid line is a V-shaped utility function in our definition. So a V-shaped utility function is constructed by connecting the two endpoints and the prior point from the dashed line. We see by doing this, we can construct a V-shaped utility function that weakly increases the objective, because the objective is the difference between any posterior and the prior point. And also, we can show it satisfies some boundedness constraint. So our theorem says the optimal scoring rule has a utility function that is V-shaped at the mean. So that is saying the utility function is linear on both sides of the mean of the prior. So to implement this kind of scoring rule, we can simply ask the agent a binary choice question. So we can ask the agent whether you believe the mean is higher or lower than the prior mean. So that's posting two options for the agent to choose. And after that, when the state realized, the agent is getting a score that is linear in the realized state. Next, I'm going to talk about the multidimensional problem. So first, I will show the approximately optimal scoring rule and a statement stating the comparison between separate scoring rule, which is a common practice, and the optimal scoring rule. So here's our design of multidimensional scoring rule. So we say a scoring rule is max over separate if there are single-dimensional scoring rules S1 to Sn with convex utility functions U1 to Un, such that the score is given by the dimension that the scoring rule, the single-dimensional scoring rule, has the highest utility function. And for this max over separate scoring to be bounded and proper, we require each of the single-dimensional scoring rule to be bounded and proper. How to implement this? To implement this, the principal simply posts single-dimensional scoring rules on each dimension of the assignments and letting the agent choose his favorite dimension to report. By looking at our example in the beginning, we can see separate scoring rule is really bad. So this is the formal definition of a separate scoring rule. That is giving single-dimensional scoring rules S1 to Sn, and the final score is simply the sum over the single-dimensional scoring rules. And we have seen in the opening example, the approximation ratio of separate scoring rule can be as bad as the order of n. So this is saying the common practice in real life is not good. And we also prove our optimal max over separate scoring rule achieves 8 approximation to the optimal objective value. So the interpretation of this result is you don't want to make the agent make separate reports or make separate decisions on each of the dimensions. We want to link the decision, and this is better for the principle, which has been observed in previous auction literature. OK, I guess that's all for the paper, and there are some related works. So previously, there are a line of research characterizing the proper scoring rules. So for eliciting full distribution and eliciting the mean, and also characterizing the set of elicitable properties. Like, for example, the variance is not elicitable by a proper scoring rule. And there's a very old work by Osborne trying to maximizing effort with the class of quadratic scoring rules. And there is also an independent work of ours, which tries to maximize effort in a binary state model with costly samples, and the effort level are integral. There are several follow-ups of our work. Like the first, Chen and Yu, they consider optimizing a max-mean objective without knowledge about the prior and signal. And Kong considered optimization of peer prediction mechanisms. We also have a we also have our own follow-up work generalizing the model to multidimensional effort, and I will be talking about this in a workshop tomorrow. And another paper also accepted at EC this year consider expected budget constraint and limited liability. So here are the results in our paper. In this paper, we propose a framework for optimizing scoring rules with binary effort. And we characterize single-dimensional optimal scoring rule. We also propose approximately optimal scoring rule for multidimensional report space. And we show some comparison between some commonly used scoring rules to our optimal scoring rule. For example, the quadratic scoring rule for single-dimensional space, we show this is far from optimal, but it is optimal in the sense of prior independent. And like I said, the separate scoring rule is far from optimal. We also have sample complexity results for designing the optimal scoring rule. And that's all for my talk. Thanks. I'm happy to take questions.
Thank you, Yifan. Yeah, time for questions?
Actually, what's the intuition for the result that you can, any complex scoring equation just equivalently written as just to like your two-line segments in the one-dimensional case?
You mean the intuition behind the result that the scoring rule is posting two choices to the agent?
Right. Well, that is equivalent to write it as just like this, like piecewise linear.
Yeah. So I guess there are many interpretations of this result. So firstly, you want to maximize the incentive given to the agent. So let's say a connection to the auction literature. So you can see this kind of a program, it is linear in the scoring rule. So for a linear program, the optimal solution is usually at the boundary, and the boundary is sort of linear scoring rules. And also, like as I said, to get this kind of V-shape scoring rule, the V-shape is augmentation of any convex utility function for our objective because we are maximizing the difference.
Okay, so essentially the claim is it's a linear program, therefore you have to meet the two endpoints, that's for sure. And then you also have to be minimizing them.
That's
so
right.
The simplest thing to do is just
Okay.
Thank you.
Mm-hmm.
Yeah, I'm wondering, like, this hinges quite a bit on the principle knowing the prior exactly, right? So like if the prior is slightly wrong, then like, you know, this like linear thing really breaks down. You mentioned this with the like this V-shaped thing is no longer a good choice at all.
So yeah, that's a good point. Very good question. So to implement our optimal scoring rule, the principal only needs to know the prior. But like we have the result for our sample complexity result. Like when you estimate the prior from some samples, you might have a error from the estimation of the prior. So in this case, the principal is suffering from an additive loss, not a multiplicative loss.